Hello, everyone. My name is Eric Lanz. I've been a software engineer for about 15 years, doing iOS work for 10. I currently do SDK engineering for Embrace, but I've also worked in the gaming industry, finance, healthcare, communications, all kinds of things. I was a member of the WatchKit team at Apple for 3 years, but I'm most proud of the year I spent living with the Zenkoji monks in Nagano, Japan. And today we're actually having two speakers because we have a two-part webinar. The first part is going to be on sort of using user sessions to debug issues, and the second part is on how do you build a system like that on the back end. And the engineer who'll be presenting that section is my coworker, Juan. He's a back-end engineer at Embrace, and I'll let him introduce himself more fully in his section, but that's Juan. So for me, what we're going to talk about today are first, what are user sessions? What do I mean when I say that? Why should you care about that? Why is that important? I'm going to show you an app that me and Juan built, and then I'm going to show you a bug that our CEO immediately found in that app, as you know, that's what CEOs do. Then I'm going to show you how I use the user sessions that we included in this application to hunt down and figure out how to fix that bug. And hopefully that'll be enlightening to you on what user sessions are. And then I'm going to hand it off to Juan, and he'll show you some things you need to think about if you want to build a system like this for yourself. Okay, so first, what is a user session? Well, when I think of a user session, I'm thinking about everything that that user did from the time they launched the app to the time they stopped using the app. Now, that might mean they put the app in the background, that might mean they force killed the app, but the point is you want to capture all of the data points between the time they launched it and when they stopped that session. And you want to capture those into your backend so that you can look at them later in some kind of dashboard or some kind of database form. But when we're in dev, before we go to production, we don't need that because we have these tools right on our computer. We have the console app, we have Xcode, we have these great tools that are going to help us figure out all these problems. The people who are finding these bugs are probably in the same room with us. They might even be sitting right next to us. We can just grab their phone, look at it, reproduce the issue. It's generally a lot easier, I think, to fix bugs when you're in dev. That doesn't mean all bugs are easy. You know, of course, there are still really challenging bugs that you have to deal with when you're in dev. But generally, I consider that to be easy mode because you have all of that context kind of sitting right there, and you can talk to that context and query it and debug it. It's very easy. When you move into production, things are going to change. And they're going to change because the people using your app aren't sitting there anymore. You can't just talk to them. So you have now millions of people all over the world using your application, and you can't just go and talk to them. Moreover, they're not going to give you great bug reports. You're going to often get things on the App Store like a 1-star review. It's just going to say, you know, the app is bad, or I couldn't log in, or the screen loaded to white, something like that. And you're going to have to try to figure out these bugs from those reports, and maybe you'll have an email address or a username, but you're not going to have a ton of context unless you set something up ahead of time to make sure that you have that context when you need it. And that's what user session data is all about. So right now, today, we probably think of user sessions mostly as those crash reports that you're getting. And you know, fortunately, both platform holders, Apple and Android, Google, both provide really good out-of-the-box crash reporting. This is iTunes Connect. iTunes Connect will slice and dice your crashes from your app any way you want. You can look at them all. You can see which ones are important, which ones aren't. And probably like you can get all the crash data you want from iTunes Connect. And if that's not good enough, there's a lot of other third-party services that'll handle crashes. But crashes aren't the full story of what a user session is. And that's what I'm trying to say today is a user session needs to be enough detail for you to figure out what happened. If a user makes a report that their app loaded to a white screen, that's not going to have a crash report. There probably won't even be a session in iTunes Connect for that because nothing went wrong from Apple's operating system point of view, yet the app didn't work at all from the user's point of view. So those are the kind of bugs where you really need user session data. You need that logging. You need, like you see here, you know, the user was on this window, then they moved to this window. Here's a screenshot. Like these kinds of data points of how the user journeyed through your application are going to help you figure out those bugs later on. But at the same time, you don't want to have too much data in there. If you just log every single thing that happens, then you're going to be going down a lot of wild goose chases when you hunt down bugs, just because there's so much data in your user session. So let's summarize what we've talked about. When you're building your user session data and you're thinking about what you're going to send from your client to your server so that you can look at it later, think about things that only the client would know. So you might have great server logging already, but what happens if the client rejects an SSL certificate locally because of an MDM profiler or something like that? Your server logging is not going to tell you that happened because the request never left the client. Only the client knows that happened. So think about things like that, that only the client knows, that you can then combine that information with your server logging to get a full picture of what happened. Think about third-party SDKs. So you probably use Facebook or Google to power features inside of your app, yet those SDKs could have bugs. They could be slowing down your app, they could be causing deadlocks, and they could be causing crashes. So when you're planning a system like this, think about your usage of those SDKs and make sure you have adequate detail tracking around that too. Then think about aggregation counters and rolling up your data. And what I mean there is, like, don't just record all of this raw log data in a SQL database and then query it. That's not really going to help you very much. Like, what'll happen there is you'll get into a raw session and then you'll run into a problem, like you'll see a 404. And you're going to want to answer a question of how many people is this happening to? And it's going to be hard to answer that question if you have to write a custom SQL query every single time. So Juan will go into this in more detail in his section, but think about creating, lookup tables and roll-ups so that you can answer those questions that you're going to ask quickly, and you don't have to, figure out how to answer them in the heat of the moment. And don't just redirect your existing login stream to the server. So your app probably logs tons of info, things that help you in dev, but think about all of those log statements when you're trying to solve a problem in production. Like, a lot of those are just going to be noisy. They're not going to make a lot of sense, or they're just going to be repeated in every single session. And maybe collapse them into one. You don't need all of that detail. And the same thing for user events. When a user's scrolling on a table view, you don't really need to record every single UI touch event that's happening in that gesture. It's probably good enough to just record the start point, the end point, and the duration of the gesture. Depending on your app, some apps probably do want all that detail, but most apps probably don't need it. And the bottom line is, when you're putting some detail into your user session, think about how you're going to use that data later. If you can't think of a way that it might be useful, maybe don't include it. Okay, so now that we understand what I mean by a user session, I want to show you an app we built. So Juan and I built a recipe tracking app. It's pretty simple. You log in and you get back all of your favorite recipes. You can browse the internet and mark more recipes that you want to save. It's a cool recipe tracking app. It has an interesting login system that I think most people are familiar with, where we hit a login endpoint first with a username and a password. We get back an access token. Then we include that access token in our post to further endpoints, and then those endpoints will, go to the database, load that user's data, and return it. So that's kind of how the app works with the server. And then we have, of course, the typical Facebook, Google SDK smorgasbord in there too. So we used Embrace for our user session tracking. Shouldn't be too surprising. I work for Embrace. But at the same time, the reason I chose it is because it captures that networking automatically. And when we built this app, we were most worried about that login scenario, because if a user can't get to their homepage, they're going to think the app is broken. And that's like the most frustrating thing for users. So I was really worried about that. So I wanted a user tracking system that automatically captured all the networking, so that I wouldn't have to do a lot of work for that. And then I also added a little bit of logging around all the code branches and choices that a user might make in the app. Then I was really proud of this, and I showed it to our CEO, Eric, and of course, he tried his account and it logged to a white screen immediately. So it didn't log into like a partial home screen. It was just completely blank like this. The app didn't crash. So I wouldn't have had any kind of crash report or anything like that. He was standing right there and showed this to me, but it was the release build of the app from test flight. So I still didn't have great logging, and I couldn't just plug it in and look at it. I know his username, and really, I know now everything I need to figure out this bug. I know the username of the person who did it, or at least enough information that I could figure out who it was. I know the time that it happened because he was standing right there. And I know kind of what happened, that it was this white screen. And that might not seem like enough, but I'm going to show you now how that little bit of information is actually enough to go and figure out what went wrong. So to the hunt. So for this next section, I'm going to be showing you screenshots of the Embrace dashboard and the real data that our application produced in there. So this section is going to be pretty interesting. You're going to get to see our real data. So this is the Embrace dashboard. It's a website, and what it does is it talks to our backend, and all of the data that was recorded from the application is then visible in this website, and we can query it and look at it and play around with it. And so the first thing I did is I went up to that search box at the top and I typed in user ABC. That was our CEO's username. He used that in tests, I don't know. And I found his session. So he had 4 sessions, and I know that the issue he hit happened during this session because I was standing right there, so I knew the time that it happened at. So what I'm going to do now is I'm going to click on that session and we're going to look at its detail. And so this is what user session data can look like when you look at it later on. So what I'm looking at here is from top to bottom, all of the events that my application logged with the backend, and now they're visible in the dashboard. So these are things that the client decided to log in the backend, and they're in time order. So you can see right at the top, I've got this green arrow here where the login call happened, and that got a 200 OK. That's great. And here's where the homepage call happened. I have this breadcrumb here. I'm going to load the homepage. That also got a 200. So interestingly, like I kind of expected to see a 500 or a 404 for the homepage, given that he didn't see any content. But actually, his session looks okay for that. But down here, we see a 404. There's something maybe wrong with the product images endpoint. I'm not sure exactly what's wrong with that. But it's interesting enough. Let's take a look at that 404. Maybe that's our bug. Now, like I said before, when you see something like this, what's going to happen now is I'm going to start investigating this 404. And the first thing I want to do is try to figure out how many people is that happening to? Is that 404 something that's really common that everyone sees? Or is it something that only our CEO saw during this session? If it's something only the CEO saw, maybe it's related to the root cause of the bug and I should investigate further. But if it's something everyone sees, it's probably not related to the root cause of this bug, or it might be, but let's take a look. But what we're going to do now is we're going to move over to the aggregate data that Embrace stored. So what Embrace has done is Embrace sort of looked at all of the session data from our application over a few weeks, and then it sort of said, okay, during that time, your app actually 40% of all of the endpoints you call got a 400 error. And so what I'm learning from this aggregate is right away, I probably don't need to dig too deep into this. There's still a bug here, but it's probably not the thing that my CEO hit because 40% of my users are getting this bug. So if it was something where it was causing that white screen, then 40% of my users would be reporting a white screen error. That's not happening. So I'm already pretty comfortable putting this aside, but let's go one step further. And so in Embrace, I can now click on that aggregate rollup and I can see all of the paths that were called that caused the 404 error. And you see a pattern, they all have this same path, product images. And in fact, like I said here, as soon as I clicked into this, I realized what I did wrong. Juan had actually given me an endpoint called product image, not product images, and I typoed and put the S there when I programmed it. And so all of our product images are failing to load in production, which is bad. But that wouldn't cause the home screen to be completely empty. There would still be the framing content of the home screen, just the product images wouldn't be there. So we found a bad bug, but it's not the root cause of our CEO. And the aggregate data in Embrace helped me to sort of stop going down that rabbit hole. And now I can come back out and try to find that root cause again. But I'm kind of at a dead end. So what I'm going to do is I'm going to put my thinking hat on. I'm going to go through what I know and see if I can come up with a better theory. So I know the user sees a white screen on login. I know it wasn't a crash, and I know it wasn't a network failure because I saw the 200s in the session. We did find that typo in the network call, but it seems unrelated and it seems to happen to everybody, so it's probably not the real problem. I'm going to teach you a trick now that I always use when I get to a dead end like that, and that is to compare what I'm seeing with a baseline run. Now, what I mean there is I'm going to compare this bad session that my CEO had with a good session. Now, I could generate that good session by just running the app myself and performing the same actions that the CEO does. Sometimes that's useful, but actually Embrace captures all of our good sessions too. It's kind of a cool feature of Embrace that it doesn't only capture the sessions that ended in a crash or a bad networking call or something like that. It will capture perfectly clean good sessions too, specifically so that you can use them as a baseline. So let's go find one. So in Embrace, when sessions are captured, they get flagged with things that happened in the session. So this one had a networking error. This one ended in a crash, but this one has nothing. And the thing is with iOS, like having a networking error doesn't necessarily mean that the user had a bad experience with the app. It's bad and you should fix it, but there's a lot of times where memory warnings happen, networking errors happen, images don't load, and the user really doesn't even notice. So it's actually not that uncommon to see a lot of sessions with icons like this. But when I'm looking for a baseline, I'm looking for one that had none of that. And the reason is because I want to give myself the best possible chance of finding a really good baseline to use. So what I did is I looked through Embrace sessions and I tried to find one that had no icons. And so this one looked good. And so now what I'm going to do is I'm going to put that good session. I loaded, two web browsers, put them right next to each other, and I'm trying to line up the login calls and the homepage calls. And I'm trying to see if there's any difference between these two sessions. And remember, this is what a good one looks like. This is what a bad one looks like. And since I already know that kind of the home screen didn't load, I'm going to look at those calls specifically. And so Embrace captured more data than we see here. So what I'm going to do is now click on all 4 of these networking calls, get their detailed information, and then put that right next to each other. So that's what we've got here. So we've got the detailed bad login here, and the detailed good login here, but both are actually the same. Both got 200, it's almost the same bytes in, out. That's our token size. The good one was a little faster, a little slower, but really that's just networking variance. I don't think I can make a judgment call on that. So the login calls don't seem to be teaching me much. The homepage call is more interesting. There's a clear difference here. Like something is obviously different, but let's look in detail what that is. So if I look at this, the difference seems to be this duration. So the good call took about 2 seconds and the bad call took only 10 milliseconds. So on the surface, how does that solve our problem? Because you think networking faster is better, but let's think about the way our application actually works. The way this endpoint really works is it takes an access token, and then it goes and loads the content from the database. That should take a while. So if this endpoint is returning quickly, maybe it couldn't do that work. So now I have a theory. I have a theory that something was wrong with the access token on this homepage call. And even though I got a 200 response, it returned much too quickly to have actually gone and loaded any data. Whereas we see here in a good case, it actually takes about 2 seconds to load data. That's a little slow, and I'll talk to Juan about that later. But still, I think this is good enough to now go to the code and try to validate this theory. And notice I didn't jump immediately to the code. I feel like if you do that, you're kind of going to confuse yourself. It's almost always better to use your user session data to come up with a theory and then go to your code with that theory and try to validate it and work that way. So that's what I'm going to do. And I'm going to kind of jump ahead here just to save some time. That actually was the answer. And so what I did is I went into the code, and these 2 blocks of code are in 2 different parts of our application. This is where we make the login call. We dispatch it to the global queue so it doesn't block the main thread. And this is where we make the homepage call, and we do the same thing here. And you see that when the login call returns, it sets some token data, and then that token data is used when the homepage call is made. The problem is these aren't connected at all. So when I dispatch this and dispatch this, they're just racing. And if the login call is fast enough, like in a dev environment, this code might work. And in fact, here you can see that someone, when they were working on dev, maybe me late at night some night, actually noticed this problem and put a little delay in here. And that little delay was good enough in dev. This probably worked just fine on my dev computer all day long, but as soon as I put in production, that delay is not good enough anymore. And what's happening is the login call is not finished before the homepage call starts. So this variable is nil. This call is failing but it's not failing in the HTTP sense because the home page does exist. So the HTTP server is like, yeah, 200, but the application server is like, no, there's an error here. But we have no error handling. We just directly load whatever it returned. So we have a couple of bugs. We have a race condition and we have no error handling. So let's summarize now what we learned. Because what I've shown you now is I've shown you an app, shown you a bug, shown you how I use this awesome user session data we had to go and figure out what that bug was. But we also learned that not all bugs are crashes. And if you only think about crashes in your app, you're actually missing out on the most frustrating scenarios for your users, which are scenarios where the app freezes or doesn't load content. Because the reality is, if your app crashes, a user knows what to do. They click the icon and launch the app again, assuming they want to keep working with your app. But if the app freezes or doesn't load content, users don't know what to do in that case. Should I wait a little bit? Should I furiously tap on the screen? Should I, send it to the background, bring it to the foreground? Users will try all kinds of things, but it's very frustrating for them. So if you only think about the crashes in your app as affecting your users, you're missing out on this whole suite of other kinds of crashes that are bugs that are significantly more frustrating for your users. Second, HTTP servers can return a 200. It doesn't mean your app's going to work. Like the 200 HTTP error just means that the HTTP server fulfilled the request, but the application server behind it might not have. So, don't have race conditions in your networking and check your networking errors. I also learned that from this. You need to have this good session data to compare with. As you saw there, we got to a dead end pretty quickly in our investigation. And if we had not have had a baseline to look at, it wouldn't have been obvious to us that there was a difference in how the homepage performed. And then finally, this user session data was critical to debugging this production issue. If I had not have had this, I would probably still be trying to reproduce this on my dev computer today. But the reality is, because I had that user session data, I was able to go and do this investigation, come up with a theory, and solve the bug without wasting a bunch of my CEO's time or wasting a bunch of my own time. Okay, so I hope you enjoyed this section. I hope I've convinced you that this kind of thing is worth having. Now I'm going to hand it over to Juan, and Juan will give you some insight into some of the considerations if you want to try and build this kind of system for yourself. So over to you, Juan.
All right, just give me a moment while we transfer over screens. All right. Cool. Hi, everyone, and welcome to the second part of today's webinar. Sorry, I'm working from home, and I think we're having the janitor come by the by the hallways making some noise. So I'm gonna mute myself for a couple of seconds while he passes over.
You guys have any questions, feel free to go ahead and type it down in the box below. We've got a couple that came in already. Again, we'll answer them at the very end of this webinar. Or maybe we can answer some of them now while we wait for Juan to get on board. Eric, we did have a question that came in. It says, do you have any advice for logging inside a user session, and how much should we include?
Oh, sure. So this question comes up a lot. It's basically related to that idea of when I'm implementing user sessions for the first time, should I just redirect all of my NS log stream, or maybe I have a logging framework like Lumberjack or something like that. Should I just redirect everything in that to my backend and use that as my user session? And I would say no. And the reason is twofold. One, a lot of those logging statements are info logs, and they're going to be redundant in every session. And so if you include them in every session, they're just going to kind of fill up your backend, but they're not really adding any extra data to that user session. They're not going to help you fix a bug. So just filtering them out is going to save you money on storage costs and not really cost you anything in lost data. And the other point is, if you're just sending up strings, that's less useful for you when you go to do aggregation and rollups. It's better, like think about this. If you have a login statement that says something like loaded image a.png with bytes 256, that's a string. If you put that into your backend, you're going to have many variations of that string. They're not going to compress well, and you're not going to be able to query on them. If instead you did that login as a JSON object where you said loaded image, and you had a property image name, and you had a property file size, then you could start to aggregate and query on those properties in your backend. And suddenly your user session is this data-rich thing that you can query and compare and work with, and not just a bunch of strings. I hope that helps answer the question.
I think it did. I got a thumbs up from the person. So, all right.
All right.
I think when you're ready.
Yeah. Hi, everyone. Sorry about that. Welcome to the second part of today's webinar. Today, I'll be talking about how we built a scalable backend for the network monitoring tool that Eric was using earlier to debug his mobile error. So I'll start off by talking a little bit about myself. Cool. So again, my name is Juan Cabrillo, and I'm a backend engineer here at Embrace. And I work here primarily with our data store. So, spoiler alert, this talk will be about Clickhouse, the primary backend that we use for our network monitoring. And just as a little fun fact about myself, I was the first eng hire here at Embrace almost 4 years ago. Here's the overview of today's presentation. First, we're going to talk about the requirements that we're going to have for our backend system. And then we're going to distill those down into the evaluation criteria that we'll use to look at our architecture and figure out what's going to work for us. And we'll talk about the different data stores that we looked at. First, we used MySQL for our proof of concept. Then we used Cassandra to make it scale. And then finally, we used Clickhouse to make our architecture much more simpler. I suspect that most of you haven't heard of Clickhouse, but we really like it here at Embrace. And I hope that this presentation will be a nice little intro to it. And then we'll close out this part of the presentation with a little demo. Okay, so these are the requirements for our backend system. We expect to ingest billions of rows of network data a day. And if you think about your network applications and, mobile applications, and you think about how chatty they are, the number of network requests that they make within a single session, and you multiply that by the number of users and how often they open the application, that's going to end up being a lot of data. So we need a system that can handle just tons and tons of it going its way. We also want to be able to power the dash that Eric saw that had both highly aggregated counts, but then you have the ability to dig down into particular issues. And the way we're going to do that is that we're going to have long-term storage that has aggregates, and we're also going to have short-term storage to find particular examples of those issues. We want our dashboard to be performant. We want things to become available as quickly as possible. So we want fast writes. And we also want our dashboard to be powered in real time. So we want those queries, those reads to be very fast as well. And then as a separate maintenance cost, I can imagine some of you might be thinking, whoa, that's a lot of data. Like, how are you gonna keep all of that? Well, what we're gonna do is all that highly granular stuff, that's only gonna be useful to us for a very short period of time. We're mobile developers, we iterate very quickly, and things from a couple of months ago are gonna be less useful for debugging than the things that happened within the past week. So we're gonna want to have a way to age out the granular data, but the trend data, the aggregate stuff, we might wanna keep that around for a few months so we can do comparisons for the health of our app over longer periods of time. And this is the proposed schema that I was talking about, the short-term and the long-term storage. And here you'll see that in the short-term storage, a single row corresponds to an individual network call. So we have all that good stuff like duration, session ID, a bunch of other information we might need later. And then in the long-term stuff, all that individual information goes away, and instead we roll it up by hour, and then we ultimately have counts. And the short-term stuff is the stuff that we're gonna want to eventually age out, but the long-term stuff we're gonna keep around for a while, maybe on the order of a few months. So now that we've considered our the requirements for our backend system, we're going to distill that down into 4 evaluation criteria. And as I mentioned earlier, we're going to want performance so that we can look at all that data and still get something that returns to us fairly quickly. Since it is a lot of data, we also don't want our storage to get out of hand. So we're going to want something where it's not going to be too expensive for us to keep that information. Hopefully, and this is not just true for this project, but for any project that you work on, you want to keep the complexity down to a minimum. So when we come up with the different systems, we're going to make sure that it doesn't get too out of hand. And finally, since we have those 2 tables, we're going to want them to be consistent with one another. And that's actually something that we ended up iterating on. And you'll see that it was ultimately Clickhouse that helped us get around this consistency problem. So first we had to come up with a proof of concept. And what's everybody's favorite database? It's MySQL. It's been around for a very long time. All of us in-house were already familiar with it. And we knew that for a proof of concept, we could use it to get something standing. And it's pretty straightforward. We could actually map the schemas that we wanted to work with the things that I proposed earlier on, right? It's very straightforward. And this is the architecture diagram for our first implementation that used MySQL. So individual network information came through to our writers, and then they were immediately written to short-term storage. And then to calculate aggregates, we used an aggregation cache. In this case, it was Redis. And then we had other writers periodically read from them and then write the aggregated counts to long-term storage. And we also had a cron job that would read stuff from the short term and then age that out. So, we got this to work. We managed to pull the thread through with the system, but there's already a few issues with it. And if we look at our evaluation criteria, the good thing about this is that it's very simple. We got something to work, but if you guys looked at our initial requirements, the amount of data that we expected to be coming our way, it was simply not going to be performant enough. MySQL is not really meant to handle this much data getting thrown at it. The other issue is that MySQL doesn't have great compression, especially because it's going to have row-oriented storage. And I'll elaborate more on that in a later slide. But we knew that in addition to performance, storage was going to be a problem. And finally, for consistency, that second path, the one that goes through the aggregation cache, that could introduce consistency problems. Not only are those, points of failure, like if Redis were to ever go away or if the writers became unavailable for whatever reason, you can start getting discrepancies between the aggregates or the information that you show in your short-term storage and the information that you have in your long-term. So this is something that we're going to have to figure out. These are the things that we're going to want to address with another data store. So at this point, our very first priority was make this performant. We want this to be able to power our dashboard in close to real time. And we looked around for a few other options, and the next one we looked at was Cassandra. And Cassandra had, boasted really great performance and great compression, and it seemed to answer a lot of the problems just up front. And as a nice to have, Cassandra allows you to set TTLs on your tables so that you, as I mentioned earlier, we use the cron job to age out data in MySQL. In this case, when you create a table, you can tell Cassandra, the data stuff here, that's going to age out in 3 weeks. The things from here, that's going to stick around for a few months. So it seemed like Cassandra was going to answer a lot of our issues just up front. It's pretty modern, it's pretty cool. And the reason that Cassandra is so performant is that it takes a completely different approach to data modeling. And the reason for that is that it asks you to denormalize your tables. And what that means is that MySQL, you typically take an approach where you want to normalize all your data. And amongst other things, what that means is that you want to prevent duplication of your data as much as possible. And generally this is a good idea. That means if you don't have data duplication, you don't have to worry about consistency, and you minimize the amount of storage that you have. You just write things, once if you can get away with it. And your approach is typically that you have, a single common table or as few tables as possible, and those can answer as many queries as you can. So one of the things that we want to look at when we're considering the health of a particular endpoint is see how many 400s we're getting over a period of time. And we can see that this common table can answer both of those. We can get the number of 400s, and then overall we can just get the number of all counts. And this is good. This, you can get the information that you want, but you can make this faster if you take a different approach and you denormalize your data. So we can take that common table on top, and instead of having all of it, we can split that information into 2 dedicated tables to answer just those 1 queries. Here we'll see that now we have a dedicated 400 counts table, and we have a second table that has the overall counts. And the advantage here is that when you're filtering, when you're looking for 400s, you have to filter out way less rows because you already know this stuff is pre-aggregated and it's going to be closer to what you want. If you have a common table, even if you have a very good query engine, you're still going to have to do some work to figure out which are the rows that you want to read out and do aggregates on them. In this case, all that stuff, you put it up front, but your queries are going to be much faster. And this is the approach that Cassandra wants you to take. If you look at their data modeling approach, you typically work from the queries that you want to do, and then you make the tables for them. So how did that change your overall architecture? Well, now you see the main difference is that now in Cassandra, we have way more tables, and as a result, way more writers to maintain them. And this was a step up from using the MySQL approach. We definitely got the performance boost. Cassandra is still very performant. And Cassandra, I mentioned that it denormalized the table, but Cassandra does compression very well. So even with some of the data duplication that we had, our storage was a lot better than if we had used MySQL. But now we introduced a new problem. This system is much more complex. If you think about it, network data has lots of ways that you can slice it. You might want to look at counts from the domain level, domain and path, maybe look at things for one particular status, or want to group all your 500s together. There's tons of different ways that you can slice and dice it. And each time you want to create a new query, you have to introduce a new table if you want to keep that performance. So we have this increased performance, but now it comes at the cost of complexity. This is much more complex than our previous iteration with MySQL. And the other thing is that we still haven't solved this consistency problem. If at any point the aggregation cache or those rollup writers ever went away, we would still have that consistency problem. So we're hoping that the next data store, the next solution that we come up with, hopefully we can still keep those performance gains. We can still have great storage, but now we should try to address that complexity and the consistency. And we looked around, we did our research, and what we found was Clickhouse. Like I said, I suspect most of you haven't heard of Clickhouse, but I really like it. And when my friends ask me about it, I tell them MySQL, Clickhouse is like MySQL, but it's much faster. It's like MySQL on steroids. And like Cassandra, it's got great performance. It has great compression, TTLs, all that other stuff that we had before. We got it. But it has 2 different features that make it really stand out. One of them is that it stores data with a column-oriented approach, and that's going to make our queries fast, but still make our tables simple, so they still look a lot like MySQL. And then the other feature that it has, which makes it very powerful, is that Clickhouse does automatic rollups for you, and that's going to really simplify our architecture. I should mention that there's no such thing as a free lunch, and Clickhouse doesn't allow you to do transactionals, or they're still working on that, but it's not a primary feature the same way it is in like MySQL. And Clickhouse is not really meant to do a whole lot of updates. And as you'll see, this ultimately ends up being fine for our use case. So first, column-oriented storage. I pulled these slides from the Yandex website. Sorry, not these slides, these animations. And you'll see that this is what highlights the difference between row-oriented storage and column-oriented storage. In a row-oriented approach, which is MySQL, all the information for a particular row is stored together in disk. So if you want to read 3 columns out of a particular row that has 20 columns, even if you want just those 3, you're still going to have to read out the entire row. And this is going to be slow. You're going to incur a lot of overhead just reading out that information out of disk, and then you're going to end up throwing most of it away. So comparatively, it's going to be a lot slower than a column-oriented approach, where all the values for the same column are stored right next to each other in the disk. And this is great because not only does it give you fast reads, but since all that data is going to tend to look the same, if you have like dates, strings, chances are you're not going to have too much variety within your column type, and you're going to be able to get gains there with compression. You can come up with, Clickhouse already has some good compression schemes, and then you can implement your own if you'd like. The second feature from Clickhouse that makes it so powerful, and this is my personal favorite, and these can have their own dedicated webinar to them, but Clickhouse has these things called materialized views. And the way you think about them is that a materialized view is a listener that you put on a table. And what happens is that as you write rows to it, it'll ingest them, it'll perform some kind of aggregation, and then write the resulting rows to a new table. So if we take a look at here, again, our short-term and on the long-term tables, we're still writing the individual network calls. You'll see that they have granularity to the second. We have the information like duration and session ID. And as these 5 rows get written in, the materialized view will pick them up and perform the aggregation that we want. In this case, we want to roll everything up to the hour, the URL, method, and status code, and we want to do the counts. So it'll take those rows, automatically roll them up, and put them in our long-term storage for us. And this is great because now we've pushed all the aggregation logic and work to Clickhouse. We no longer have to maintain it ourselves. And the great thing about this is that now it really simplifies our architecture. If you look at this is ridiculous simple compared to the other one. That second flow, the one that went through Redis and then our other writers, that's just completely gone. We can now push all of that to Clickhouse. And if we look at our evaluation criteria, we see that we get green check marks all across the board. We get performance and storage, but now our architecture is a lot more simple, and we've delegated that consistency concerns over to Clickhouse. So it's really simplified our architecture, and it's allowed us to satisfy our demands while making it simple for us. And so the takeaways for this is that, one, we started out knowing MySQL. This is, I'm pretty sure everybody's seen it when you're taking a CS course, an introduction to database, but we had to get out of our comfort zone and try tools that we weren't familiar with. This was the first time that I was working with either Cassandra or Clickhouse, and I learned a lot about how they worked and what were their ideal use cases. The second takeaway is that you really want to understand how that data store works so you can figure out its ideal use case to evaluate its limitations. And then that kind of feeds into the last point, which is that you have to use the right tool for the job. I really like all 3 tools. I think they all have their place, and we actually use all 3 of them at Embrace. We use MySQL with our Django applications, and for anything where we need to manage state, where it's really important that all of that stuff happens within transactions. So we have MySQL for that. We use Cassandra for fast lookups for really large blobs in our system, but we use Clickhouse to do aggregation over a ton of metrics. So all these 3 tools, they're great, they're pretty robust, but what you have to know is how to pick the right tool for the job. And now I'm gonna show you a little demo on how Clickhouse works. I'm gonna pop out of here. Cool. This is my this is a Clickhouse instance that I have running on my machine. It's running in Docker. And just to show you guys the schema that I have my 2 tables. I have network and network rollup. And if we look at what's in network, we have information there that captures an individual network call. We got the domain, the method, the path, all that good stuff. And we can form our aggregates. You can see counts by domain. We can get more granular and start looking at counts by domain, path, method. You'll notice that this is pretty fast, and we're processing millions of rows a second. And like I said, Clickhouse is just very performant. And sort of going back to the difference between Cassandra and Clickhouse, you sort of work your way backwards where this is this particular query, so it feeds this particular table. This is more sort of like MySQL, where you still use a single table and it can answer all your questions. So with this particular query, we can look at the network information that we have and then see if any of these endpoints have a particular problem with their 400 rates. If we take a look at here, looks like most of them are doing pretty well, but this particular combination for domain and path, this is having a lot of 400s. And if we want to find a particular instance of it, here we have a session ID, and then we can go look at our other data stores and pull up the information for that session. And you know, this is all pretty fast, but it can be faster. At this point, I haven't even begun using the roll-up tables. Again, if I were to show you what the roll-up table looks like, you know, we still have a lot of the high-level aggregate stuff, and we lost the information about the particular sessions, but that's fine because these are just the tables that we want to use for our aggregates. And if we want to take a look at, you know, the same query that we had before, you know, can we still find this problematic network call? This took out on the order of like maybe 200 milliseconds. This is just so rolled up. We still get the same results, but we get it an order of magnitude faster. So this is really great. And just to show you guys sort of how the writes work, if we were to go back and look at all the different domains that we have, you see we have these 4, and I'm going to pipe in some information that I have here and write it directly into our Clickhouse. Oops. Sorry about that. And we're going to be copying a ton of data in. I see we have this new domain. It was roughly 250,000 rows, and it was still written pretty quickly. And the best part is that we still have consistency with our rollup table. See, I know this data looks almost exactly the same, but the difference is the source. This is the information coming from our individual raw table, and then this is the information coming from our rollup table. And we've deferred all of that consistency stuff to Clickhouse. Clickhouse will just do all this stuff for you and make it fast. And yeah, that's the demo.